Hello and welcome back to Classes with Atish. We are continuing with our lectures on waves. This is lecture number 5 and today's topic is standing waves. If you have already not revised lecture number 4 on waves, I would highly encourage you to do that because there I introduced the concept of interference and that is what will be needed to understand standing waves. So with that, let's get started with this topic. An interesting fact that I do want to tell you right away is standing waves are not actually waves. Let's hold on to that thought. I will come back to that later and explain you why standing waves are not waves. Okay. Now, how are standing waves formed? Let's say we have two waves which have the same amplitude and same frequency but traveling in opposite directions. When they superimpose, that's when standing waves are formed. Okay. Now the easiest way to create two waves with same amplitude and frequency but traveling in opposite direction is by what is called wave reflection. Let me explain using an example of waves on a string. So if I hold an end of the string and the other end is connected to a wall or fixed to a wall, if I jerk it and create a wave, that wave travels through the string, it hits the wall and then it gets reflected. That's called fixed end reflection. So with that, because it has the same amplitude, same frequency, and after reflection it is traveling in the opposite direction, so we can make them superimpose. So let's say this is the wall, the fixed end, and here's a wave that I created, and that wave is traveling towards the wall. After reflection, it is coming back like this, and it is superimposing. Okay. Now notice the amplitude when it hits the wall, it gets reversed because it's a fixed end reflection. Okay. So we can call this the incident wave and we can call this the reflected wave. This phenomena is possible in strings, in organ pipes. Here you will have sound waves which get reflected and they superimpose. Okay. Okay. So for the incident wave, let's write the wave equation. So let's say incident wave is A sine omega t minus kx. So if coefficient of t and coefficient of x are opposite signs, that means it is traveling in the positive x direction. And after reflection, the reflected wave will have amplitude minus a, because as soon as it's reflected, the amplitude reverses. Sine, this time the frequency remains same, omega t plus kx, because now it is traveling in the negative x direction. Okay. Now here I just showed one wave. You can imagine that there are a series of waves. So the incident waves are still going, but then there is a reflected wave that is coming and both are superimposing. So by principle of superposition, the resultant displacement of any point on the string will be a vector sum of the incident wave and the reflected wave. So we can write this as A sine omega t minus kx plus minus A sine omega t plus kx Now let's do one thing. Let's make a table. So we would take a snapshot of this superposition that is happening. Okay. So we have the incident wave is A sine omega t plus kx or minus kx minus kx. We have the reflected wave, which is minus A sine omega t plus kx, and we have the resultant wave, say y, is yi plus yr. Okay. So now we are taking a snapshot. So by snapshot, we are fixing time. So we will investigate at time t equals 0, at time t by 4, at time t by 2, at time 3t by 4, and t. Okay. Okay. At time t equals 0, the incident wave is what? Minus A sine kx. Can I say that? Because you put t equals 0, sine of minus kx is minus sine x. So it's minus A sine kx. What about the reflected wave? This is minus A sine kx. And what is the sum? It's minus 2A sine kx. Okay. At t equals t by 4, so remember omega is 2 pi by t. So at 2 pi by t times t by 4, it's pi by 2. So A sine pi by 2 minus kx is A cos kx. What about the reflected wave? Pi by 2 plus kx. So sine is positive in the second quadrant. So this will be minus A cos kx. So the resultant will be 0. At t by 2, this is pi. So sine pi minus kx is sine kx. Sine is positive in the second quadrant. Sine pi plus kx is minus sine kx. So minus and minus becomes again A sine kx. So the resultant is 2A sine kx. So I'll just go quickly on this one. This will be minus A cos kx. This will be A cos kx. And the resultant will be 0. And at time t equals t, this will be minus A sine kx minus A sine kx. This will be minus 2A sine kx. Okay. Now, let us plot the resultant displacement along x. So we will be plotting y versus x at time t equals 0, y versus x at time t equals t by 4. So I need 1, 2, 3, 4, 5 graphs. 1, 2, 3, 4, and 5. So this graph will be for t equals 0. This will be for t by 4, t by 2, 3t by 4 and t. Okay. So if I plot this, what happens? So at sine 0, it's 0 at x equals 0. So as x increases, this will be negative. So somewhere like this it will go. Okay. All right. At t by 4, it is all points on the string have 0 amplitude. Okay. At t by 2, this will be just opposite to this. Okay. Again at 3t by 4, all points will have 0 amplitude. And at t, it will be just like how it was for t equals 0. I know some of it might have got cut out, but that's okay, you can still figure it out. Okay. So one thing to notice here is, first of all, at t by 4 and 3t by 4, all points amplitude is 0. This never happens in waves, right? It never happens that at some time all points on the string have 0 amplitude. Okay, so that's a difference. Second thing to notice, there are few points like this is one point, then this point, again we have the same point here somewhere. These always have 0 amplitude at any time. These points are called nodes. Okay, so nodes always have 0 amplitude, you see, at any time. So we can say these points never move. Okay. And then there are some other points like this. Okay, so this point, that have a maximum amplitude equal to 2a. So these points are called antinodes. But remember, these have maximum amplitude at certain times. Anywhere between t equals 0 and t by 4, it is not maximum, it is coming down. Okay? So the reason I said standing waves are not actually waves, because in waves, the fundamental concept is all points execute oscillations. But here we see there are certain points called nodes which never move. They are not doing any oscillations at any time. Any point in between two nodes, they are doing oscillations, and one of those points, which is exactly between two nodes, reaches a maximum amplitude. Everyone else, for example, if I look at this point, its maximum negative amplitude reached is only this. Its maximum positive amplitude reached is only this. It is not 2a. Okay. Only the point that is right here in the center, that reaches the maximum positive or negative amplitudes. Okay. So you have to realize what is happening. Now, if I take a video, not a snapshot, this will actually look like so this is what it will look like if I draw y versus x. So this points, if I just concentrate on one point, this is going up, coming back to its mean position, going down, coming back to its mean position. Same way, This point is going up, coming back to its mean position, going down, and this point, which is exactly at the middle of two nodes, is going up to a maximum amplitude of 2a, coming back to its mean position, again going down to a maximum amplitude of minus 2a and such. And then there are these points which do not move at all. Okay? So that is why it is called, it looks like the wave is standing. It's called standing waves. But if I really look at the definition of waves, no energy is traveling. The only energy change that is happening is going from maximum kinetic energy to maximum potential energy, coming back to maximum kinetic energy, coming back to maximum potential energy. So only change that is happening is kinetic energy to potential energy to kinetic energy and back. But that energy is not flowing along the x direction. Okay? So it is only the changes happening for that one particle. So standing wave is actually nothing but simple harmonic motion of points along x. Simple harmonic motion, okay, not a wave. So the expression for y that we would get, if I do this mathematically, we should get a simple harmonic motions expression. Let's see how that looks now. So now let's take a closer look at this mathematically. So this is the case of fixed end reflection. We can write this as a sine omega t minus kx minus a sine omega t plus kx. Now we can use sine c minus sine d as 2 cos c plus d by 2 sine c minus d by 2. So then this becomes 2a cos c plus d. So omega t and sine c minus d. So omega t minus kx with a minus. So the y net is minus 2a sine kx cos omega t. This we can say is the general equation of standing waves. Okay. So any equation of this form, y equals 2a sine kx omega t or 2a cos kx cos omega t, or it can be 2a cos kx sine omega t. These are all forms of standing waves. Okay, see how this is different from traveling waves. Traveling waves, we have a sine kx plus minus omega t plus phi. But this is of a different form. This is the form for traveling waves. This is of the form y equals a cos omega t, which is the form for simple harmonic motion, if you remember. Okay. So this part, let me rewrite this again. Y equals minus 2a sine kx cos omega t. This part is the amplitude and this is the phase. Now since the amplitude is dependent on x, so therefore we saw that at certain points the amplitude is always 0. Those are the nodes. And then at certain points amplitude is maximum. So it depends on x. It depends on x, the position of the particle. So this one we can say depends on position of particle. The amplitude is maximum at antinodes and minimum at nodes. When would amplitude be maximum? When sine kx is 1. So A max is plus minus 2a and A min is 0. When will the amplitude be maximum? When sine kx is 1 or plus minus 1. And when will amplitude be minimum? When sine kx is equals to 0. So from that we can find out the values of x at which we get the antinodes and the values of x where we get the nodes. So because k equals 2 pi by lambda, you can see the antinodes will happen at lambda by 4, 3 lambda by 4, 5 lambda by 4 and such. And the nodes will happen at 0, lambda by 2, 2 lambda by 2, 3 lambda by 2 and such. Okay. Okay. We talked about fixed end reflection. But if, let's say, the incident wave was yi is a sine omega t minus kx, if it is a free end reflection, which means when would a free end reflection happen? Let's say the string is attached to a ring and the ring can go up and down on a pole. And in such a string, if I send a wave, then it will not reflect to flip the wave. It will reflect in the same way. Okay? And then it will superimpose. So what will happen? Reflected wave will be a sine omega t plus kx. So this is free end reflection. And these two waves can also superimpose. Okay? And we will get something similar result. In this case, we will get y equals 2a cos kx sine omega t. Okay, but this also is of the general form for standing waves. And here you can see this would be the amplitude and this is the phase. And then similarly we can do a similar analysis and find out where there would be our nodes and antinodes. Okay, let's talk of one other thing, position of nodes and antinodes. So if I draw a y versus x graph and so this is how the standing wave is happening. This is 0, this is lambda by 4, this is lambda by 2, this is 3 lambda by 4, this is lambda, this is 5 lambda by 4, this one will be lambda by 2, lambda by 3 lambda by 2. So nodes are occurring in this example. So basically this superposition that we did are occurring at 0, lambda by 2, lambda, 3 lambda by 2 and such. Antinodes in this example are happening at lambda by 4, 3 lambda by 4, 5 lambda by 4 and such. For different standing waves, the positions of the nodes may be different. However, the distance between two nodes is always lambda by 2. You see, lambda by 2, lambda by 2, lambda by 2. Similarly, the distance between two antinodes so when I say distance between two, I mean consecutive nodes or antinodes is always lambda by 2. And the distance between a node and the next antinode distance between a node and the next antinode and the next node is always lambda by 4. Okay? Okay, so let's close this chapter by listing down the key differences between traveling waves and standing waves. Okay? Okay, so traveling waves would be the generic equation of traveling waves would be roughly like this. Okay. Of course, this represents equation of a traveling wave where each particle are executing simple harmonic motion. For standing waves, this is somewhat like this. Okay, so here you can see it is not a function of kx plus omega t. Okay, these are separate. Okay, this represents standing waves that are formed by two waves traveling in opposite directions, both having the same amplitude and same frequency and same wavelength. Okay, okay. So in traveling waves, energy is transferred. In standing waves, energy is not carried or transferred. Okay. Traveling waves, they travel. Standing waves are stationary. Okay. In traveling waves, amplitude of each particle is same. Okay. So each particle is executing simple harmonic motion and each particle will at some point reach the same amplitude. However, in standing waves, amplitude depends on the position of the particle. Antinodes will have maximum amplitude and nodes will have minimum amplitude, which is 0. Okay. This maximum amplitude is 2A in this case. In traveling waves, at no time all particles pass through the mean position at the same time. All particles are at mean position simultaneously. In standing waves, at certain times, all particles are at mean position simultaneously. In fact, this happens 2 times in every time period. Okay. Finally, for traveling waves, between any two particles, any phase difference is possible. But for standing waves, between two successive nodes, all particles will always be in the same phase. For illustration, if we have a standing wave like this, okay, between these two nodes, particle 1 and 2, they are always in phase. This particle and let's say any two particles you pick up, 3 and 4, they are always in phase. In phase meaning, what is the definition of same phase? Same phase means their amplitude, their velocity and their acceleration all are same in magnitude as well as direction. Between these two nodes, 1 and 2 will always have the same amplitude, velocity with direction and acceleration. Okay? But here in traveling waves, there can be any phase difference between 2 points. Okay? That phase difference can be between 0 to 2 pi. All phase differences are possible between 2 points. Okay? So those are the differences between traveling and standing waves. And with that, we will close this particular lecture on standing waves. Hopefully this made sense. I have another lecture coming up in which we will discuss the modes of vibration of strings that are fixed at both ends. Okay? So with that, see you in the next one.